nanoHUB.org.
Online simulation, and more for nanotechnology.
Today we have Ying Dan, who's going to be presenting. He is a PhD candidate and research assistant in materials science and engineering at the University of Illinois at Urbana-Champaign, with a research interest focused on studying material defects and mechanical properties of metals and alloys using computational tools and theoretical modeling. Today he's going to be talking with us about how he's used UF2 in courses at UIUC. So with that, I will hand it over to you, Ying.
Thank you so much for the introduction. So good morning, everyone. My name is Yang Dan, and I'm from the University of Illinois at Urbana-Champaign, the Department of Material Science and Engineering. So I worked as a teaching assistant from year 2021. And in this process, I worked a lot with the UF2 software. So today I'm very glad to share my experience working with UF2, as well as the fundamental knowledges of this software, as well as the finite element analysis to all of you. And also maybe I can share some experiences or thoughts on the teaching with UF2 and nanoHUB in this process. So let's get into it. So today, the webinar will mainly be divided into two parts. So in the first half, I will be talking about the fundamentals of doing finite element analysis in UF2. And in the second half, I will do a show off how UF2 works by doing some demonstration of two UF2 simulations. So in our research or some problem-solving experiences, we often encounter modeling problems or needs that we want to model systems with differential equations. So these are problems that can be that has the form like this. So it can be described by ordinary or partial differential equations, which describes how the system evolves over time or within the space, and also to be specific to the environment and specific to the questions. We may have initial conditions and boundary conditions to help us determine the solutions. So a very well-known example could be the heat transfer problem, for example, in an ideal rod, as shown in this picture. So we want to know the temperature distribution within the iron rod. And so the first thing we do is that we need to look at the heat equation, which is listed here. So this gives us the information of how the temperature changes over time and within the entire space. And kappa is the heat thermal conductivity. Yeah, and also we need to have some boundary conditions for different scenarios. For example, we can have the two ends of the iron rod fixed at different temperatures. For example, we can let one end rod dipping into the cold water and the other dipping into the hot water. So this gives us a well-set problem that is described by the heat equation and also two boundary conditions. And for different scenarios, the boundary conditions might change. For example, we instead of dipping the two ends into the cold and hot reservoirs, we might have heaters or refrigerators, let's say. So in physics, there are two kinds of heat sources. And in this process, we can have some other kinds of boundary conditions. So in this case, we know the derivatives of the temperature with respect to time and the space. And also we can have a mixture of the two boundary conditions we had before. For example, we have one end of the iron rod fixed at a fixed temperature, and the other end of the rod attaching to a heater. So we know that this is a very easy toy problem that we can easily solve with analytical solutions. But what happens in real life? For example, we want to solve something in engineering or science, which can be give us very complex systems. For example, the material that we're looking at can be non-homogeneous. For example, if we are given a non-homogeneous rod that has many different kinds of materials in space, or probably the shape of the rod is not regular. We can have irregular boundaries, or we can have very complex environment so that the heat changing process can be very complex. So this is something that can happen in real research or engineering. That's the complexity of the problem is much higher than the toy problems we just see. So one of the problems listed here is, for example, we want to look at the turbine blades, because we want to help the turbine work at higher temperatures. We want to apply some ceramic thermal barrier coatings to prevent it from the high temperatures. So one of the questions we want to investigate is that we want to know the thermal conductivity, kappa, of this ceramic thermal barrier coating. And this will help us better understand how the coating and the turbine blades work at high temperatures. And this is a very necessary process that we want to do in the manufacturing process during the quality control process. But in reality, the measurements of the kappa are very difficult. So sometimes very time consuming and expensive. So people hardly do this kind of measurements in reality in the quality control process. So how about doing calculation on this? So if we want to do the calculation to predict the thermal conductivity kappa of the thermal barrier coating, we may face some really complex situations. For example, the ceramic materials might have complex microstructures. So here I'm quoting some pictures from previous researches that shows some different kinds of microstructures that they made from different samples of the thermal barrier coatings. We can say that the microstructures can differ a lot. And in this case, we need to use some more advanced techniques to do the simulations numerically. So there are mainly two methods that people use to model the complex microstructures. So for example, people might use mean field method to simplify the problem. So the basic idea of the mean field method is that people want to replace the details of the materials with some average or effective quantities. So people will try to compute the average properties of the statistically representative microstructure in this process. And in this way, people try to understand what is happening inside this material. Sometimes the mean field method is very useful because it can provide useful bounds to calculate the effective properties. But this method can have limitations. For example, when the macroscopic properties that we are investigating has a nonlinear relationship with the underlying properties. So the averaged underlying properties might not necessarily reflect the macroscopic properties on average. And sometimes the underlying properties might not be spatially uniform. And so this makes the averaging difficult sometimes. And sometimes it is simply unclear about how to do the averaging reasonably. So for example, if we want to take some kind of average averaging microstructure, but we are not sure if that averaging microstructure will have a reasonable grain size orientations or things like that for us to investigate or to reflect the real physics of the material. And sometimes people are just interested in some properties that relies on the extreme conditions. For example, materials failure. So in materials failure, we just care about the extremes of the stress distributions, and it has nothing to do it has not too much to do with the average distribution of the stress. So we need to use some other accurately modeling method that can reflect the specific microstructures. So which comes the finite element analysis. So yeah, so this is the reason why we want to look at the finite element analysis in real engineering problems. So as we know that UIUC is trying to do the finite element analysis, and it's for some generalized problems. So here I'm trying to go into the physics of the UIUC and try to understand what the UIUC is doing. So in general, the UIUC is a software that computes the properties of materials with complex microstructures, and it can use the finite element analysis, and it is based on image. So first things first, it works on the problems that has a schematic form that looks like this, that are described by this set of equations and symbols. So there are a couple of quantities here. For example, phi are the fields, are defined as the fields, which are the functions that changes over space. And we have fluxes here, which are sigma. And the fields and fluxes are coupled by some coupling constants, which are ki here, or we call them moduli. And also we might have time-dependent fields, which makes the second equation come into play. And we also have the M and C as the coupling constants that specifies how the changing fields are affecting the field quantities. And also we might have the generalized forces, which are defined as the Fx, as F of phi and R here, where R is the space, is the coordinates in the space. So for example, so this is a very generalized form of what problems that UIUC can solve. So if we want to go back to the heat transfer problem we just talked about, we can see that if we set the M equals 0 and we let the fields to be the temperature in the iron rods, then we can say that we get the heat transfer problem and the thermal conductivity we just looked at. And this is more than that. So with this schematic form, we can solve other problems like the elasticity or thermal expansion as well. Okay. So this is the schematic form of the problems that UIUC solves. And so because I just mentioned that UIUC is doing finite element analysis based on images, so it needs to do the calculations in 2 dimensions. In this software, the material properties are always specified in 3D. So in order to reduce the problems to 2D, we need to do something here. So we need to reduce the problem to 2D when we assign the material properties to images that we are working on. So for example, we let's say we have a coordinate system where the x-axis and the y-axis are inside the plane of the image, and z-axis is just going outside of the image. So part of the things that we do is, for example, we can let the fields have no out-of-plane gradients, or they simply just don't have the z derivatives. This is also called the plane strain in the terminology of the software. And also, people can also have the fluxes determine the fluxes that has no out-of-plane components. Or let's say the fluxes just don't have the z components. So this is also called the plane stress. Yeah, so this is how UIUC tries to convert the three-dimensional problems to two dimensions because they work on the images of the materials. And also the UIUC project has another software called UIUC 3D, which handles everything in 3 dimensions. I'm not going to talk about this software here because we just want to be focused on UIUC 2, but I just wanted to let you know that there is something similar to UIUC 2 that works with everything in 3 dimensions. Okay. And then I'll go into the basic concepts of the UIUC 2 software and show how it works when solving problems. So first, there are some important concepts here. For example, the microstructure. So the microstructure is the fundamental abstract entity used by UIUC 2. So if you want to study some kind of material, we say that we are looking at the microstructure of the material and try to build our models based on the microstructure. So the microstructures are usually rectangular, as like the examples here. So they are formed by pixels, where just like images, where each pixel has the local information of the material. Yeah, so this is a figure I quoted from the UIUC 2 paper, which shows the microstructure of silicon nitride ceramic here. As you can see, that there are some structures inside this microstructure, and the dark parts are, I think they are crystalline, and the parts that has lighter colors, I think they are glassy. So these are 2 different kinds of phases here. And is UIUC 2 open source? Yes, I think it's open source. Yeah, I think it's you can search for the website of NIST, and I think you can download the manual and also the source code of UIUC 2 here. Yeah, so it's free to use. And also the tool is available on nanoHUB as well. Yep. So this is the microstructure, and
Someone asked, is the material porous?
I think this is ceramic, but I was not sure if this is porous. Yeah. I think it's the picture that shows is a combination of the crystallines of the grains and also some amorphous or glassy systems here. Yeah. Can I use it on Windows? I think this software is mainly developed in Linux and Mac OS. I'm not sure if this is, yes, this is silicon nitride. Yeah, I'm not sure if it works on Windows. Yeah. Maybe you can check the menu on the UIUC 2 the web page. Yeah. should we need to do the experiments for the microstructures? I would say you can do experiments for the microstructures, but you can also use the simulated microstructures to use as the input for UF2. Yes, it does not work on Windows natively, but it can run under WSL. I'm not sure about because I use Ubuntu in my own research. But I think they could be providing some tools that enables the UF2 to run on Windows. Yeah. Do we have to do image segmentation? Oh, okay. Yeah, probably I can just move on and address all the questions at the end of the talk. Yeah. Yeah. Thank you. Okay, yeah, so I just talked about the microstructure, and the next thing is the image, which is also a very important concept in this software. So an image in UF2 is can be, as I just said, can be an experimental micrograph or some outputs from the simulation. So in the simulation of UF2, you can use an image or a couple of images to be read by the UF2 and create the microstructure in this software. So you can use one image or multiple images to create a microstructure because the images from different processing techniques could reflect different features of the microstructure. So that could be helpful if we want to investigate different features in this process. Yeah, so that's what image does here. It can be used to build microstructures. And another thing that is important is the materials. So in the UF2 software, it is defined as the set of properties which can be assigned to the pixels. For example, in the silicon nitride example I just showed, so we can use the color property to be assigned to the pixels, which shows the different parts of the material. So the pixels are thresholded and assigned into two groups based on their color. And in this process, we can create two pixel groups so we can have a grains group, which are mainly the pixels that has dark color. And also we might have a matrix group, which has lighter colors here. So with the materials defined and assigned, and with the pixels assigned into two different groups, then we can build skeletons. So a skeleton is defined as the mesh of the finite elements. So in order to do finite element analysis, we need to divide the microstructure into the many small parts, and this is what the skeletons do here. So there are several methods that that UF2 can use to create the skeleton. I think you can either do it by hand or use some automatic ways to generate the skeleton. I'm not going into the details of here, but just wanting to know that this is the skeleton is the mesh of the finite elements that the finite element analysis is worked on. And this is only the geometry. So, and also similar to the images case, a microstructure can also have multiple skeletons based on how many features you want to look at. And here there is some interesting hierarchy of approximations here. So the actual microstructure that we are investigating can be approximated by the image or the micrograph of that we feed into the UF2 software, and the material map can be the the approximation of the image or the microstructure or the micrograph, and the skeleton can also be another approximation to the material map. Yeah. So yeah, that's the skeleton, and another concept, important concept, is the mesh. So the mesh is almost the same as the skeleton, but it is defined with physics and math. So we have physics quantities and equations that can be used and defined on a mesh. And with that, we can then define our problem and continue to solve it. Yeah, so that's the important concepts that I want everyone to know here about how UF2 works. And the next thing is the typical steps of running an UF2 simulation. So first, you need to create a microstructure, because that's almost the most important thing in the UF2 simulation. To do so, you can the simplest way to do probably is to load an image to create the microstructure. And also, of course, you can create that by hand. And also, the next step is to identify what features you want to look at in the image. And in this process, you create pixel groups that reflect these features in these images. And also, the next step is to create the materials by specifying the properties. In the example before, we assigned the color properties to the material so that the different pixels represent the grains and the matrix here. So after the materials has been created and assigned, the next step is to create the skeleton and adapt it to the image. So then we create a mesh based on the skeleton, and then on the mesh we define the fields and activate the equations that we want to use in our simulation. And after all of this is done, we can just solve the equations and get the solutions. And in the end, we can visualize and do the analysis here. Yeah, so that's the typical steps of running an UF2 simulation. So I think that's what I want to say about the fundamentals of finite element analysis in UF2. And before we go into the demonstration part of the UF2 simulations, so does anyone have any questions?
Yeah, it looks like we do have one. Which criteria is used to set the threshold to discriminate the pixels? Can it be tuned by the user?
I think it can be tuned by the user, yeah. So I think the threshold you use is pretty specific to the problem. Yeah, and I think there is automatic way of grouping the pixels based on the threshold. And I believe you also have the way to manually set that in the...
Yeah, I'll go ahead and read it to you. So it looks like I'll read both the questions because they're from the same person. On which format do you load the image? Do you use discontinuous finite elements?
Yes, I think the finite elements are... Yes, I think first it supports most of the images here, and also, yeah, I think it uses the discrete, yeah. Discontinuous. So Andrew just said that UF cannot do discontinuous elements. Yeah, sorry that probably I didn't understand the question correctly. Yeah, but I think you can trust Andrew's answer that UF cannot do discontinuous. Yeah. Okay, so the next step I will be doing some demonstrations of the UF2 simulations. So before that, I would like to say that the simulations, the the demonstrations I do are from the course materials that I use in the teaching on at the materials science and engineering courses. So so multiple courses has been incorporated, has used UIUC in our department, and we create also the class demonstrations and the course projects with the support from the nanoHUB. So these courses include the things like the mechanics for material science and engineering, lab studies, and thermomechanical behavior of materials, and the mechanical behavior of metals. Yeah, mainly based on the mechanical properties of materials. So the students' feedback with the computational modules that we use the UIUC are mainly positive. And so I think our department has done, yes, I think we can simulate plasticity in UIUC. Yeah. So the students mainly has positive feedbacks from this because they think that they are generally reliable and easy to use on nanoHUB. And previous research that our department has conducted in 2019 has shown that the students has increased in confidence in using the computational tools after the training in class. So this figure shows that the confidence of the students with different kinds of computational tools before and after each semester. And the rightmost shows the change in the students' confidence in UIUC. So yeah. So this research shows that the students are confident with the computational tools after the training. And our results also show that the UIUC software ranked as the second computational tool in students' most confident software. So just after MATLAB. Yeah. So I think UIUC is a very useful tool in our teaching. And now I'm going to do the first demo, which is to simulate the stress distribution in the crack tips in aluminum. So so in this simulation, we have two crack tip geometries. So one is blunt and the other is narrow. And we are interested in visualizing and calculating the stress distribution in these two samples. So let me open the UIUC from nanoHUB. Okay, so I think this is the homepage of the nanoHUB. And then you go to the Explore and Tools. And in the search tools, you can just type the name of UIUC, and then you can start it. And click Launch the tool. Okay, and then to starting. Okay, so after it started, we can launch a session that has the UIUC software launched as well. So what I'm going to do next is to upload our simulation files to the session. So to do this, okay. This is our first demonstration. And so first we can upload the image that we want to look at. So we choose to look at the blunt crack first. So we'll upload it. And then I have another Python script that does some initial setups to do the simulation. So yeah, let me briefly show what the script does. So in order to save time, I'm just putting some of the initial steps in as the Python command lines here. So what it basically does is the procedure that I just talked about. So first we try to create a microstructure from the image, and then we create pixel groups based on the color, and also we create and add the material properties here. So in this case, we use the elasticity information here, and then we create and adapt the skeleton. So yeah, let's get into it. So in order to set things up, oops, I haven't uploaded the script yet. Okay. Okay, so yeah, we can just run the Python script from the file and then click OK. So it will start the simulations and it will follow the commands that we just wrote in the Python script. So now it is trying to create the skeleton here through some iteration steps. Okay, here we go. So now we have set up the skeleton as we have seen from the script. And what we'll do next is to go through these items here to set the things up. Okay, so we have the skeleton. The next thing is to set up the mesh. So we can just create a new mesh here and use the default settings here. Okay, now we have the mesh. Then we can specify the fields and equations. Because we are interested in the stress and strain, so we can just choose the displacements as the field that we look at here. We first define it and then set it to active. And then we need to use the force balance and the plane stress here. Yeah, so that's how we define the fields and equations in this problem. So the next thing is the boundary conditions. Okay, so yeah, we're trying to apply look at the stress in this material. So we first apply the boundary condition of the displacement in the y direction. Yes, so this is Dirichlet boundary conditions and displacement as the field, and equation we use the force balance. So for example, we set 0.05 at the top, and we set the minus 0.5 at the bottom. Okay, and then we can set all of the x boundary conditions to 0. So for example, we can do top left here. Okay, so now we have the boundary conditions set up. And then we can go to the solver and we double click the yes, I think we can run the script without the simulation without the Python scripts. So I'm just putting the skeleton setup things in the script. So just to save time in the demo, but you can definitely do the same thing by clicking everything here and yeah, do the setups here. Yeah. So we move on to the solver, and so we first define it, and then we try to solve it. Okay, now that we have solved the problem, and we can just visualize this. So to do the visualization, we can create a new layer in the graphics window. So we want to visualize the stress distribution. So here we want to choose the category to mesh because the stress distribution is defined on the mesh, and it's a microstructure, skeleton, and the mesh, yes. And we want to use the field contour, for example, to do the plotting. And because the stress is a flux quantity defined in a nanoHUB. So we should choose flux here, and we try to visualize the YY stress in this case. Yeah, let's see if everything's good here. Okay, yes, for the rest of the things, we just choose the default settings, and here we go. Okay, now we have can simulate the stress distribution in this material, and we can see that there is some stress buildups here at the tip of this crack. So yeah, so in the student project, they are asked to explore several things using different settings, for example, different boundary conditions, etc., to do some virtual experiments. So this is really cool. So we can also make a comparison between this material and the other narrow crack. So I'll try to launch another session and simulate the other geometry here. Okay, so now I'm going to first load the narrow crack here, upload it, and then I wanted to show that using the GUI to do the settings and the Python script to do the settings are purely identical. Yeah. So this one I'm going to show you the script as well. So it basically does almost the same thing as the previous script, but I'm just putting all of the other stuff like the defining the fields and the equations and the boundary conditions, and also set the solver in the Python script. Yeah, because they are purely identical. And I want to run this script and see what happens. So here we go. So file, load, script. Oops, I forgot to upload the script as well. And yeah. Okay, so here we go, run scripts. So it will do everything, all the setups for us automatically by running this Python script. Where are only 3 boundary conditions? Yeah, I'm just demoing this as an example, but of course you can use some other boundary conditions. Okay, now it's finished. And then we can do this. Oops, I think we haven't solved it yet. Let me double check. Click the solver. I think it's defined. Yeah, it says unsolved. So we just need to click solve here. Okay, now it's solved. And then we'll do the same thing as what I showed just now. We visualize the stress distribution on the mesh. This is the microstructure skeleton mesh, and we want to use the field contour for this, and flux for the stress, the YY component for the stress, and the rest of stuff. Okay, we'll just click OK and see what happens. It's trying to plot the figure that we. Okay, yeah. So here is the distribution of the narrow crack that we just see. So as you can see that the Python script and the clicking and setting things up in the graphical user interface are just typically identical here. Yeah. So that's our first demonstration. And we still have a bit of time, and I think we can move on to the next one. Yes. Okay, yeah, so here I'm just putting the simulation figures here which is the same as you just saw. And the second simulation is a kind of similar to the first one, but with a little more details because it involves the thermal expansion and the thermal and the temperature stuff here. So yeah, this is a scenario that the students are need to do in the computational report. So which says that there's your lab has a technician. So he comes up with a great idea to improve the alignment during the compression testing of a specimen that has a shape of a dog bone. So we use the slots in the sample, which are defined, which are shown as the orange circles here. And we want to replace these traditional clamps or pins with the new pins here, which can be a circular slot or a diamond slot. And we know that in this process, it may create some thermal expansion things or some small thermal gradient across the sample. And you want to do the complex and expensive and time-consuming tests. So in this case, we'll just need to do the simulations of finite element analysis and see if see the stress distribution in the specimen, and see if there's a stress concentration points in the specimen. So yeah, let's launch another simulation here. Okay. So yeah, similar to the previous demonstration. For each of the specimen, I also have an image that shows the microstructure. So I'll try to upload this first, and then we also have a Python script that helps us do the pre-processing things. So I will also show you how what this script looks like and what it does here. So basically, it still follows the consequences or the basic steps of the WOOF2 simulation. So first, it creates a microstructure from the image that we just uploaded. And then we create the pixel groups because we have the sample part and the pin part. Yeah, that has different colors, and we create and add the material properties. So here we are interested in several properties. For example, the elasticity, and the thermal conductivity and the thermal expansion. So I just introduce, I just define and set up the properties here. And after this, we, similar as before, we create a skeleton and a mesh. Yeah, so that's what the script does. So yeah, I'm trying to run this script to set up the material properties and the skeleton and the mesh here. Okay, so here we go. So we can check that we have a microstructure here, we have materials set up, and finite element. Yes, we have a finite element mesh here. So the next thing is we want to define the fields and equations. So yeah, we want to look at the stress. So we need to define the displacement first. And also we want to investigate the thermal stuff. So we want the temperatures to be here. And in this case, let's set them to both to in plane. And for the equations, I think we need force balance for the mechanical stuff and for the heat equation, yeah, for the thermal stuff. And now we have the fields and equations, and then we have the boundary conditions here. So because the shape of the specimen is quite long, and we define that the x direction is along the specimen. So so first, let's create new boundary condition so that we try to apply a temperature gradient onto this specimen. So we set the temperature and heat equation. For example, for the left-hand side, we set it to 300 K, apply it. And for the right-hand side, we try to apply a small temperature gradient, for example, 300.1. Okay, now we have the boundary conditions, and then, yeah. Yes, I think we can specify the fields and normal boundary conditions as well. And for the solver, yeah, we just define the solver using its basic default settings. And then we click solve so that it is solved. And then we can do the visualization of the stress distribution with the temperature gradient. Yeah. So we have the microstructure, skeleton, and mesh. We have field contour. And yes, we want to measure the x-axis component of stress. And click OK. So here we go. So yeah, this is the stress distribution in this specimen. Yeah, I think we are running out of time, but I think the simulation for the others specimen is the same. So I'm just skipping the steps, simulation steps here, and we just look at the results here. So it looks like there is some stress concentrations in the pinpoint here, which might not be good. So in the teaching process, I think the students were asked to do several kinds of investigations or explorations with different boundary conditions, for example, with different temperature gradients. And they will try to make the reason about which plan they think they need to adopt here. So in this case, WOOF2 with the finite element analysis can help them do virtual experiments here. Yeah. So I think that's the basic things I want to talk about today. So we had the fundamentals of WOOF2, and also I did some demonstrations to see that the how it works in general. But probably I was missing some points in the boundary conditions. Yeah, but yeah, maybe we can add it. But yeah, we're running out of time now. So in the end, I would like to share with you some useful resources like the WOOF homepage, which contains the everything we need for the WOOF2 and WOOF 3D, and also we have the WOOF2 user manual, which is also can be seen on the web page as well. And also, I think the WOOF2 team has the paper and some slides that helps people understand how WOOF2 works, and also there are some very useful resources on nanoHUB, like the user group, and also some slides or talks that happened before on nanoHUB. Yeah, so that's all I want to share with you today. And thanks for your attention, and I'd be happy to take any questions. Yeah.
Great. Thank you so much, Ying. We appreciate you taking the time to speak with us all today. Thank you, everyone, for attending. And thank you to the tool authors from NIST who were in the chat helping answer questions, Andrew and Steve. We really appreciate that. Since we are at time, I'm not seeing any other questions pop in. I think we can go ahead and end it here.
Okay, thank you.